Well, I will try to. You have to announce the. I think I have half an hour. Yeah, but you know that all professors are scheduled to start speaking 1 hour and a half. My daughter always says that. No, please don't ask nothing to my father because he will speak 1 hour and a half without stopping. So, well, I will try to to keep in touch. And I will not speak about very sophisticated things. So I apologize because I will use classical logic. See, yeah, I am a mortal of, say, of the past century. So I will use the classical logic. And I was thinking, I had a question for before for Aldo, because I remember that phrase, that sentence, that very wise sentence, the man who said that about the non-contradiction. Well, it suffices to stay on at the entrance, at the door of the house, waiting to pass the death, the funeral of the opponent. So the question is simply a message. Have you tried to compare this paraconsistent logic? Because it's also static. That's the problem with logic. And currently, Carlo Cecchini introduces dynamics in logic. So, but say you can change your actions with time, and there is the notion of open systems in logic. So I have this question: is a way also to recover paraconsistent logic? Well, my talk has nothing to do with that. So I will speak about, say, the mathematical problems arising from this kind of objects. Well, this is just a drawing. I picked this from this publication. There are other pictures of ion channels that are better, but well, I will just take this as a motivation. So what the mechanism is simply a cell membrane, and there is these proteins, and well, ions are coming from one side to the other one. And well, that's the mechanism, and I have to apologize also for another thing. Let me explain. I have to apologize also for being phenomenological. Because in my opinion, when one works with the, I am trying to draw with this, but I cannot. Okay. When one starts with a small system of knowledge, here we have at the interior of this small system of knowledge, we have, say, ab initio models or systems. But everything is in motion, so we have to consider the relations with the environment, all things which are not known. So our theory starts to grow up in between this relation. But for the first arrows I draw there, we have no other possibilities than to be phenomenologists and to use phenomenology to derive new ab initio principles and say first principles. Yeah. So in this question of biological models, the problem is that there is no first principles yet. And so to start trying to discover some laws, one is forced to use a little phenomenology. So some basic questions about about the mathematical challenge. There is first a question, problems connected with model construction. That is, I will try to be consistently using open systems theory. So for open systems, what we need is first to say what are the observables and the states, the time and space scales, and we have to take care of the relationship with the environment. So we need to understand the interaction of the main system and the environment, which is in mathematical terms, that corresponds to our noises or martingales, say, the characteristic of our martingales. Well, and the second family of problems I would like to address is the consistency of models. Can we deduce one from each other by changing scales? Oh, there is a, I wrote that in Spanish. Scales and relations between the observables or limiting procedures. Or are they fully incompatible? So that's another family of mathematical problems. And the third family of problems I would like to address is the qualitative analysis of those models. So the question of steady states, the equilibrium, the zero entropy production, non-equilibrium, metastability, resonances, and so on. So how do we classify them? And so we find in this question of ion channels a hierarchy of models. First of all, the macroscopic model for an assembly of channels. So I wrote there this generalized Hodgkin and Huxley equations, which was discovered in the 50s of the past century, in 58, that was proposed by Hodgkin and Huxley, but based on, say, the theory of circuits simply. So this is a macroscopic family of equations. And well, there we I didn't wrote, say, the specific function f he used, but this was the first, say, the first attempt to describe the function of the neurons. And well, it has, I think this kind of equations is well known for people working in mathematical models in neurosciences. So this is a first macroscopic model. But let's go to a macroscopic models for single channels. So for a single channel, the preferred model has been a jump process, birth and death processes. So there is those drawing there. This picture is the record of the intensity of the current of ions which are going through the ion channel. And well, if one simplify a little this process, one can take, for instance, a Markov chain taking two values, say 0 or 1, or 0 and the maximum value of the current. So this is a two-state Markov chain with which remains completely specified by the birth and death rate. Okay, so that is very well known. And so, referring to the problems I raised before, we ask for the compatibility of this single channel model with respect to the macroscopic equation of Hodgkin and Huxley. So, are they compatible? Because we are working at there is one scale which is the one of a single channel, and we have in a neuron we have a enormous quantity of channels, and we would like to know if we can go from one to the other one, as I was mentioning. Well, so the answer for that is yes, because under suitable hypotheses, which ensure the propagation of chaos and the law of large numbers, in the sense the propagation of chaos as Denis used to apply. Well, this is true. That has been worked out by Pacdaman, Thiolin, Michel Thiolin, Sophie Baron-Rive, among many others. So that is so we had compatibility or consistency between the two macroscopic approaches at different scales, of course. Well, but so let's go inside the channel. And so there we can look for Langevin type equations to analyze the mechanism here in this equation. You see, well, we put the equation for the voltage for a single channel up, and the x there is a sort of, I put there, position of the gate in the channel, in the gate activated channels. There are some amino acids which are playing the role of a gate, say. Here we are thinking about the potassium channel. So you have the say the motion of this gate, we are calling that the xt. Well, indeed, one has to associate that with the energy of the ligands. I think. Well, Germán knows a lot about that, so he will give the precise interpretation of this xt. Well, and you see here we are taking this picture. Let me make a little oh, well, now it's like so it's simply like that. I am taking a 2-well potential, so we are thinking about going to this attractor or jumping to the other one. Okay, so well, let's come back here because yeah. So there you have in this double well potential, there is a height which will depend also on the voltage. And well, the relation with the environment at the interior of the channel is simulated, say, by the Brownian part there. Well, so let's ask again about consistency of this equation with Hodgkin and Huxley. So are mesoscopic Langevin equations compatible with HH? That is, does HH appear as a limit of diffusion type process dynamics? And the answer is yes, under suitable hypothesis which ensure propagation of chaos again. And that was a work done by my former student, Mauricio Tejo. Well, so now we can address a criticism to this model, which concerned the role played by water inside the channel. Because it's not clearly stated. There is a sort of friction term, and the problem with that is that most probably one lost, say, the Markovian character. And so let me make a brief passage through a class of non-Markovian Langevin-Volterra equations. In a work done with my colleague and friend Carlos Elizama, we started investigating the following picture. Think about your ion going through the channel, and well, this ion is submitted to an enormous quantity of, say, vibrations, but indeed is not only vibrations, because along the channel there are some other ions which are exerting a sort of friction force. So you have to consider, say, a friction force, and we imagine this friction force as, say, the impulsions given to the ion by an enormous quantity of little springs, but not linear springs. No, with some different, how do you call that, restitution coefficients. So they are not the typical spring one put in the, say, in courses of ordinary differential equations, but they have a restitution force which is a given F. I put it somewhere. I didn't put it there. Well, oh yes, there. You see the friction magnitude F. So that will induce the friction, but also the characteristic of the noise. And the noise, as you see there, the noise is given then by this covariance there, which depends on the V, on the F. That is, V is the cosine transform of F squared, which is connected with our springs. Okay? And so, well, the first result is that there exists a continuous version of this zero mean Gaussian process with that covariance. And this is a wide class of noises because you can well, here you have, say, take the same U as before. Here you can solve then this equation with this term, which carry the non-Markovian character, and this is the force, the friction force, say, which opposes to the motion of the ion inside the channel. And this is the noise. But this is a Gaussian noise which is not Markovian, no more Brownian. And well, on the other hand, this is a wide class of noises which includes a class of fractional Brownian motion. For instance, here, I have a problem with my file. I think. No. No, it's not a problem with the file, it's a problem with the projection. Well, so. Okay, yes, so here, oh, I don't know why it's, there it is. So the fractional Brownian motion with Hertz coefficient h equal to 1 minus, oh, it's completely crazy. This thing is completely crazy. Well, I will simply, wait a minute, I will simply turn this off. Yeah, okay. So, I don't know why it's. Yeah, so let's see if I succeed in going forward. No. Okay, there. So there you have the simulation of the solution of those equations for a fractional Brownian motion. You see, and so you start, well, there are different values of the parameters, but this oscillatory behavior shows that the current, which will be a function of this, will provide a simulation of the current along the ion channel. Well, so the current research is the compatibility or the consistency of these models, so which are non-Markovian, with Hodgkin and Huxley. This is well, a research in progress with Alexandre Richard from INRIA, who works in the team of directed by Denis. Well, so what techniques can we offer to analyze ion channels? That's the main problem for people working in stochastic analysis. Well, of course, we have our interesting martingale methods. We have also, inside martingale methods, we have the martingale problems, central limit theorem, diffusion approximation, the law of large numbers, ergodic theory, the statistics of sensory data. We have also the qualitative or geometric analysis of stochastic dynamical systems, the stochastic particles approach, stochastic numerics. We have also the algebraic stochastic analysis, in particular quantum Markov semigroup. Because, well, there, what we can try to provide is contraction of models and qualitative analysis too. And well, so with a little help of phenomenology, the big challenge is to construct microscopic or quantum models. That is, we have the macroscopic one, as I mentioned. We have already some mesoscopic models, and now we would like to go into the microscopic models. And the question will be, try to have a sort of a continuous passage from different time scales and space scales from one model to the other one. We look for consistency, and we look for applying the qualitative analysis of all those models to understand the biology, the biophysics, the biochemistry, which is inside those ion channels. Well, and so some hypotheses one can put just to try to create some toy models. Well, the first one is the ions move jumping through n sites on a given graph, which includes the channel. Well, okay, I know that's a simplification. Yes, I am simplifying. I am, but let's look for the most elementary picture. The second hypothesis, the motion is ruled by an electric field applied to the protein and perturbed by the amino acids at two different levels. Firstly, at the interior of the protein, and secondly, at one extremity of the channel, the so-called gate or selectivity filter. It should be called more properly the selectivity filter. Well, and 3, the motion of the amino acid at the gate is slower than the previous ion dynamics. It corresponds to a diffusive quantum quadrupole dynamics. Okay? Okay? So let's try to do something with all these assumptions. And well, let's try to find some Markov picture out of all this. Well, we take a complex Hilbert space. I am just introducing, say, the typical tools of quantum Markov semigroups. I can go a little quicker there because Franco was reminding yesterday all these notions. So I will take the typical Gorini-Kosakowski-Sudarshan-Lindblad generator of a quantum Markov semigroup. And we will try to play a game of giving some approach, some toy model for these dynamics. So we take the typical creation and annihilation operators, the position, the position operator, and well, here I will use 2 representations of those operators. So here we will take this representation with the L2R with that measure. And well, we know that we can also take the little L2 representation for those operators. There is the other representation. And so what happened in the intracellular vestibule generator, in the intracellular vestibule, the generator is simply an harmonic oscillator, nothing more than that. So there we have our harmonic oscillator, which is interacting with the observables. Well, and I take then that generator has a steady state of this form. That is something which is well known, especially in quantum optics. They use that very often. And then here I am doing something which is absolutely phenomenological. The other one was obtained, the harmonic oscillator can be obtained through stochastic limit or weak coupling limit, and what. So that is a very well-known example. But here I am putting, in the Lindblad part of the generator, we are considering that the creation and annihilation, well, our L case, our coefficients Lk of the Lindblad generator are now of the form, well, QAQ or QA, if I take the star. And, well, this is simply a mathematical game. One can prove that there exists a minimal quantum Markov semigroup for that. Well, but where is the beef? Huh? You will ask, where is the beef? here. Can we do something with that? So one starts performing the classical reduction of this. That is, we write the generator in this form, and we will choose a particular observables, not any x, and take. Well, so I continue to write in this form the generator, and so we will apply the CCR relations to the observables of the form f of q. So the functions of the position, and doing a little algebra, what you obtain after your little algebra is this. That generator over those observables has this form. And notice here, this part is interesting. And so let us interpret this, because this means that this generator over the algebra generated by the position corresponds to the generator of a diffusion. This part is the drift. And look, the drift is of the form of my previous U, a two-well potential. And, well, so what we can say is that the semigroup restricted to the abelian algebra generated by the position operator coincides with the generator of a continuous Markov process Qt. Well, which correspond to a stochastic differential equation of this form, which is of Langevin type. Well, and that means that this is simply a game to obtain somewhere a double well potential. Well, if one starts simulating this, you will also have this behavior of metastable behavior. This metastable behavior we observe in the two well potential. Another example, and this was taking, this was a model proposed by some researchers who are working just in the description of the of what happened at the interior of the ion channel. And but these people propose not this indeed. This is the this is my interpretation of what they propose, because they wrote a birth and death process, and they were working with the diffusion approximation of that birth and death process. But if you take this harmonic oscillator, this leaves invariant the algebra generated by the position again, and so you get an Ornstein-Uhlenbeck process. This Ornstein-Uhlenbeck process was obtained by these people. I cannot remember the name of these researchers. That was obtained as an approximation of a birth and death process. But the birth and death, you can get this birth and death with the same quantum generator. It suffices to take the other representation And well, if you take the other representation, you get there the generator of a birth and death. But it's always the same. It's always the same quantum Markov semigroup generator, which is describing what happened in this toy model of the vestibule generator. So, to conclude, my aim was just to show different mathematical problems, which different mathematical challenges, which are originated in ion channels. Because there I presented some different models at different scales, which are, say, constructed using different tools in stochastic analysis, from the classical Markov chains with two states, at the mesoscale, the Langevin equations, and at the microscopic scale, well, say quantum Markov semigroup. I also propose some non-Markovian models for the mesoscale. Well, but the question is, what for? That is, the main questions are to analyze the behavior of these models. In the case of ion channels, we are in a non-equilibrium dynamics. So it's a prototype of non-equilibrium dynamics. So we have to go further in that kind of goals. We have been working with Franco Fagnola a long time in the, say, in the best specification as possible of what we mean by equilibrium in quantum Markov semigroup, as to include the case of classical Markov semigroup. Well, in ion channels, one finds a sort of metastable behavior. Of course, the metastable behavior is there as a main characteristics of ion channels. But up to now, well, there is a theory of metastability for classical stochastic dynamics. As one version of this theory has been done by our friends in Brazil, Eulalia Vares, Antonio Galvez, together with the Italian team, with Olivieri in Italy. And on the other hand, there is a new way to work with metastability. For instance, Anton Bouvier, working from the point of view of potential theory. We are now exploring another possibility with some collaborators to connect some, say, the metastability with resonances too. Because in my opinion, resonance, the phenomenon of resonance has a very natural explanation inside the theory of open systems. you need to analyze resonance in that framework, in my opinion. But well, up to now there is a large literature about resonance for quantum systems, but with within the framework of closed systems, looking for poles of the resolvent, or well, working with some other tools. Well, for instance, with Claudio Fernandez, we introduced long time ago the notion of spectral entropy to analyze resonance for Hamiltonian systems and connected with sojourn times. Well, but I am convinced that is by means of the open system approach that one can provide a good definition of resonance. And so we hope that we will contribute to the analysis in this case too. Well, so first open research program concerns mathematical consistency of different open system approaches to ion channels. The QMS provides an algebraic tool to deal with different quantum and classical processes. Thus, it could provide an adequate framework to compare different Markov models of ion channels dynamics. But that's not all. Unfortunately, however, this mathematical tool will not be appropriated if one considers memory effects, which play an important role in neuroscience. Thus, one needs other ways of stating non-Markov dynamics. Change of noises, perhaps? So that's all. Thank you very much. And I will put here some, just a final image, because you see, I think that ion channels are a particular case of an ion trap. Nature invented ion trap before us, so that they can be put in relation with quantum optical experiences on traps. And that is something which we have been discussing with Geronimo and one of his students. And there you have some references. Thank you very much.
Thank you, Rolando. I have been working in biochemistry since I entered the first year, 1981. And these systems are very, very complex. Mm-hmm. I think that there are more simpler systems that can be solved with the same formalism. So I'm talking about very small proteins that the functioning, the distribution of entropy or energy, or how the energy flow from the solvent toward the protein and then toward a substrate, etc., is not yet well understood. So I think Ramon Latorre is not going to like this. These systems are too much complex. I think that the hope of this is in a small, very small protein. Mm-hmm. This protein have, I don't know how, 1,000 atoms, mm-hmm. And there are or 10,000, I don't remember. There are very small protein that can be treated, and you can. I think that the hope will arise from that. Mm-hmm. It's very complex.
Yes, I agree with that. I think in mathematics we have to be modest about that. And I am convinced that from interdiscipline, from that is the knowledge of nature together with other specialists, motivate very sophisticated problems in mathematics. That's my message to students, is always to look for problems outside mathematics. Mathematics does not finish in itself. And so I think that we will enjoy you.
Yes, tomorrow I will show a very simple system. Yeah. And another thing that I have been observing throughout those samples, that the physical object and the physical chemical phenomenology should be precisely defined in order for us, the people that work in biology, biochemistry, physics, to interact with mathematics. So that is another suggestion. You need to know precisely the object that you are analyzing. So you did mention some amino acid or some diffusive quadrupole dynamic. You show it should be known which is the exact physical object that this mathematics point towards, so we can interact.
Yeah.
Other question?
Thank you, Rolando, for the very interesting talk. And I just wanted to comment that this, in 1985, probably, Otto Dickmann, Johannes Metz, and Matt Gillenberg used semi-group theory also in an attempt to formalize and unify mathematical models for population. And it's not the same idea, but the aim to unifying and finding first principles and building from a basic structure of mathematical symbols and structures to build up all the models for population dynamics, structured populations, asymptotic dynamics, and try to describe. In that case, the impact of this model has been large, but more in the application setting, more in phenomenological way. But in mathematics, I think they developed a whole theory for positive semi-groups, these sun-star semi-groups that work in different spaces and dual of spaces, and develop a whole mathematical theory of being born from the application of thinking on population models and this unifying thought. I think it's very interesting. I think in biology, we need unifying principles, and this approach is very interesting. Hopefully, it will give fruit to more ideas.
Thank you.
What it wasn't clear to me in your presentation was what was that you were trying to predict precisely? You were trying to predict the behavior of the current, the opening and the closing for that particular ion channel, because let me give you some framework for my question. You went into doing the modeling and then doing the non-Markovian approach because of the kind of resistance that water can put in the channel and so on. But I was wondering if actually when you include the resistance and non-Markovian approach, you get a better approximation to whatever you are trying to predict. I mean, how you talk with the time series of the membrane. I mean, how you know that you are getting better and better results, or that you are far away from it, or so.
Yep. Yeah. Thank you, because I forgot to say why I was looking for consistency with HH or with the Markov chain records of one ion channel. The fact is that we need to concentrate on our observables and our observables are at present only at the level of the single ion channel, thanks to this technique of patch clamp. Patch clamp measure the current of ions. So there you have the experimental data. And so whenever we produce a model, we have to cope with those experimental results. That means that we have to, with our mesoscale model, we need to produce, say, the same records than the experimental one at the other scale. The calibration or of the model. But methodologically, that means that we cannot say that our models at the different scales are the model of the phenomenon. No. The only thing we can say is that we cannot exclude that they can work at that scale. You see? So, for instance, I didn't, well, I can write over this here. When we took the XT, which was connected with the motion, say, of our gate, well, the intensity of the current of ions will be a function of this. More, so this is our observable, this function of the XT. And well, for instance, in statistics, there is this method called the hidden Markov chains. So statisticians have been applying hidden Markov chains to the records of IT taken on the patch clamp, and they try to say, well, so they say that perhaps they do not obtain the XT, but they obtain some other Markov which is hidden behind their experiences. So you see, that is the relation. That is, we need to go towards the experiments, and there is a whole scale of checking, checklist.
No, thank you again.
Thank you. On a perdu le...